Peter, I have a line integral for you. Evaluate this integral along curve C from the origin to 1, 1.
A line integral? Sure. I just need to parameterize the curve and plug everything in, right?
Here's your curve. Good luck with that parameterization.
Holy crap! Look at all those sines and cosines. That's more wavy than the ocean on a windy day. Okay, so I substitute x of t, y of t, compute the derivatives, multiply everything out. This is going to take forever.
You'd be computing dozens of trig products. It's essentially impossible by hand, but there's a better way.
Please tell me there's a shortcut. My brain hurts just looking at this.
Conservative vector fields. A field f is conservative if it equals the gradient of some scalar function phi.
So the field is just pointing in the direction of steepest increase of some function?
Precisely. If we can find that potential function, the integral becomes trivial. But first we need to check if our field is conservative. The test for f equals p comma q. Check if the partial of p with respect to y equals the partial of q with respect to x.
That's way simpler than integrating. But why does that work?
If f equals gradient of phi, then p is the x partial of phi and q is the y partial. Take cross partials, and they must be equal by Clairaut's theorem.
Mixed partials commute. I remember that. So if the test fails, there's no potential function.
Let's check our field. P equals 2xy plus y squared. Q equals x squared plus 2xy. Take the partials.
Partial of p with respect to y is 2x plus 2y, and partial of q with respect to x is also 2x plus 2y.
They match. The field is conservative. A potential function exists. This means our integral is path independent. No matter what crazy curve we take, the answer only depends on the endpoints.
So all that messy parameterization was completely pointless?
Completely. Now we just need to find the potential. Integrate p with respect to x to get x squared y plus xy squared plus some function of y. Differentiate with respect to y and match with q.
The prime prime of y terms cancel out, so gay is just a constant. The potential is x squared y plus xy squared.
The fundamental theorem for line integrals. The integral equals phi at the endpoint minus phi at the start.
Phi at 1, 1 is 1 plus 1 equals 2. Phi at the origin is 0. So the answer is just 2?
Exactly. All that terrifying curve and the answer is 2.
Wait, this is just like the fundamental theorem of calculus. Integral of the derivative is the difference of values.
Now you're getting it. The gradient is the multivariable derivative, and this is its fundamental theorem. Follow for more.